Okay. Shall I begin or
Your volume is very low.
okay? How about now? Is it better?
Little better, but still, I think it's low.
Does it make any difference?
Yes.
Okay, so this is better now. You can hear me
Yeah.
better.
This is
Okay, good. So then, shall I proceed?
yeah. Sure.
Okay. Hello, everybody. So we will begin the lecture today on topic of what is sometimes called as forward error correction coding, uh, also known as simply channel coding, or oftentimes also called as noisy channel coding. So this will be in contrast to the topic that we studied yesterday, which was noiseless channel coding. So in contrast to that, we are going to cover the topic of the noisy channel coding or forward error correction coding or error control coding or simply channel coding. Okay, so this is the fourth topic of our series of lectures. And so far, we have looked at the basics of information theory, digital communication. We have seen some basic definition of information in terms of the entropy of the informative source. And then we have looked at some elements of uh, data compression or source representation, source coding, or noiseless channel coding. This is the topic that we covered toward the end last time. Yes, I'll make the presentation full screen. Just a reminder. Okay, so this is the next topic which we are covering today is the topic of noisy channel coding. And in terms of the block diagram, let me just give you the block diagram right away. This, as we have seen several times prior, is the overall block diagram of the communication transceiver. Yesterday we looked at the source encoding and source decoding. Specifically, we saw how the variable length and the fixed length codes can be assigned to different symbols that are generated by a discrete memoryless source. We saw how those assignments can be graphed in terms of a binary tree, especially when those assignments are binary in nature. We saw that there are certain assignments which reserve unique decodability. Those are called prefix-free assignments. And we don't want to do any assignment that is not prefix-free. That is one thing that we mentioned last time. And then we say that for prefix-free coding, prefix-free source encoding, Kraft's inequality holds. And an interpretation of Kraft's inequality is that you should assign to each symbol a binary string whose length is equal to negative log base 2 of the probability of that symbol. But then that we have in the previous lecture defined it as the information generated by the occurrence of that symbol. When we define the information corresponding to the occurrence of a symbol, we were not concerned with its encoding representations, right? We were just defining that information content as a mathematical entity. without practically having any use of it. But it made a lot of sense that we want to be able to define information in a quantifiable manner and in a manner such that the generated information is inversely proportional to the probability of the occurrence. Draft inequality kind of makes it practical, makes it something that is relevant to our daily life. It says that if you do proper encodings, then you will end up defining the bit strings whose lengths are equal to the information that is generated according to this definition. And once you do that, you are going to compress or you are going to represent the output of the informative source in the most efficient manner, which actually equals the entropy of the source. So that is the theoretical basis of source encoding. And we saw one example of it, which was Huffman coding, which comes quite close to the entropy bound, at least in this example that we considered yesterday. So today we are going to do the next topic, which is the channel encoding and channel decoding, which is this topic of forward error correction coding, error control coding, or noisy channel coding. Okay. Now, before we get into this topic, let me just tell you why this is just like data compression, which we motivated it as highly relevant in today's times, right? All of us kind of not only consume, but we generate a lot of data all the time, right? We don't think twice in turning on a video camcorder and taking video of some scenery if we are doing some sightseeing, or taking video of some family gathering, etc. And then we have to store it somehow, and that is where we run into some limits. Our hard disk becomes full, our USB drive becomes full. If we have some storage online, then we keep on getting messages that, okay, you are reaching your limit in terms of how much you can store on this particular cloud server. So storage is something that we have to use efficiently, and that is what the data compression source coding attempts to optimize. This next topic of channel coding or error control coding is also equally practical and equally pertinent to all of us, which is that we want to try and convert a channel which is going to introduce errors in what we are transmitting or even what we are storing into ideally a noiseless channel. And the motivation is clear. If the channel coding works in this ideal manner, then although the channel is throwing a lot of disturbances, you as the end user will never perceive it. And for example, one of the 5G service targets is remote surgery, and their precision is highly critical, right? If the surgeon is operating some instrument remotely, that communication link better be highly reliable, because otherwise the surgeon might be thinking that they are using the equipment in this manner, but the equipment might get used in some other manner, which could be catastrophic. There are many other examples. Some are mission critical examples. Some are even finance or industrial automation related examples where the accuracy of the messages that are being transmitted is paramount. We not only want to transmit large amount of data in a short amount of time, but we want to make sure that the channel better not introduce random errors. But that is fact of the life. The real world channels are always going to introduce noise. They are always going to introduce corruption, interference, etc. So how to do this? Now, one metric that we will use is signal to noise ratio that we have defined earlier, I think on the very first lecture, PS over PN, signal power to the noise power. The more specific statement of the purpose of channel coding is to say that the actual physical channel may have a poor SNR. The signal to noise ratio might be low. But the noisy channel coding or the forward error correction coding converts this channel into an encoded channel for which the effective SNR actually becomes better, maybe even good. Okay, so that is the goal, or that is the statement of this particular design topic. Now, if you think about it for a moment, it seems like this is not really practically possible that the channel is introducing the noise. How can you suddenly remove it? If you look at the Bayesian model of information transmission, where we looked at binary symmetric channel whose block diagram is shown over here. So the reason why the receiver is having problem whenever the channel is noisy is because of this red colored cross connections whose weights are P, meaning that the bits get flipped with the probability of P, right? If P is, let's say, 10, 0.1, then what it means that if you are transmitting 1000 bits, then on average, about 100 bits will get flipped. Another 900 bits may come out fine. Now, if the channel is already flipping the bits, what can you do? Right? Let's say some channel is having a good SNR, so it's effectively the P value is small, maybe 0.01. And so out of 1000 bits, maybe only on average about 10 bits get flipped. Some other channel might be kind of bad, so for it, the P value might be 0.3. So out of 1000 bits that you're transmitting, maybe as many as 300 bits get flipped. So then that is what it is, right? I mean, the 300 bits are flipped. What else can you do with it? Now, this engineers realized a long time back that, well, actually we can do something. We can indeed do something. The basic technique that the engineers had in the early days was take this binary symmetric channel and hopefully turn it into something like this, the one that is shown here. Input is still binary. The output somehow has become quaternary. There are 4 possibilities of the output. Okay. The green arrows are present horizontally as it was for the binary symmetric channel, and the red arrows are also present. But you will see one distinct difference between this channel versus this channel. Over here, when y is equal to 0, when p is, let's say, 0.3 or 0.1 or even 0.01, can you say with certainty that x is equal to 0 when you receive y equal to 0? That is the question I'm asking you. When you receive y equal to 0, can you say with certainty that x is equal to 0? The transmitter sent bit 0?
Sir, students are unable to speak.
No, yeah, so I see the response online. Yeah. So I think that is the right answer because of this non-zero value of p. When y is equal to 0, there is some chance that x could be 1. There is maybe hopefully a greater chance that x is equal to 0, but we cannot rule out that x is equal to 1. That is uh, the case study that we looked at, right? When we suspect that we have certain disease, we go and take the test result comes out negative. There is still a chance that maybe test was faulty and the person actually does have disease. So in this type of channel, we can never be sure that x is definitely not equal to 1 when y is equal to 0. Same way when we receive y equal to 1, there is some chance that x is equal to 0 in addition to x being equal to 1. But now, let me ask you this. In this particular case, when y is equal to 0, 0, will the receiver ever think that x is equal to 1? No, because y equal to 0, 0 could have been caused only by x equal to 0. Similarly, if it gets y equal to 0, 1, the receiver knows that even 0, 1 could have been caused only by x equal to 0. Same with other two possibilities. 1, 0 and 1, 1 are caused in this particular diagram only by x equal to 1. So on the face of it, it seems like this is still a noisy channel because there is green and red colored arrows. But the red colored arrows are really not noisy in fundamental sense. They don't confuse the receiver. Anytime the receiver gets any one of these 4 outputs, it knows with certainty what value of x was transmitted. And so this is really not a noisy channel, although it seems like it is a noisy channel. So the art of channel coding is to turn the Bayesian diagram for the binary symmetric channel into a diagram that looks something like this. Okay, so now, but how to do this, right? I mean, this is simple enough for me to draw something like this, but in engineering practice, how to get it done? And so I'll show you something very, very basic in terms of noisy channel coding scheme. And maybe after 5 minutes, hopefully you will tell me that, yeah, something like this is actually done by this basic scheme, which is called repetition coding. The entire idea of repetition coding is that you don't just transmit one bit at a time. Whenever you have a bit to send at the transmitter, you send it a total of n times. Okay? You actually have only one bit to transmit, so this is the numerator of this ratio R. The denominator is how many times you are actually transmitting that bits. So you have only one information bits and you are transmitting effectively n encoded bits. So the rate of this code is 1 over n. In general, for the topic of channel coding, the rate of any channel code is the ratio of the number of information bits to the total number of encoded bits. For this particular case, it is 1 over n. Right? Simple enough. Let me give you an example. Suppose you have a 6-bit information sequence that you want to transmit. If you didn't do channel coding, you would send these 6 bits just like the way they are shown here at the top, 0, 1, 1, 1, 0, 1. Suppose you decide to do rate 1 over 3 repetition coding. So what will you do is, you will take 0 and repeat it 3 times, because n is equal to 3. Next bit is 1. So you will again repeat it 3 times. And then 1 again 3 times. You end up transmitting total of 18 bits like this. Although you are sending 18 bits, actually you are sending only 6 bits of message. The total number of bits being sent is 18, and so the rate is 1/3. Now let's see what happens if you send this 18 bits over binary symmetric channel and it randomly flips some of these bits that have been sent. So the one in the red have been flipped. Okay. Now, my question is that suppose the receiver knows the boundary of these 3-bit blocks, right? So it will take each block of 3 bits at a time and then proceed with it. My question is that at the receiver, suppose as shown in this example, for the first block, we got 001. What should the receiver do? Should the receiver say that bit 0 was transmitted or bit 1 was transmitted? Yeah, bit exactly. So somebody said majority voting would be the right approach, which is actually the case. So for the second block of 3 bits, we would say bit 1 was transmitted because 1 is in the majority. Similarly, for the third one, we will say bit 1 was transmitted because again 1 is in the majority. So repetition coding is simply you repeat the transmitted bit multiple times, and at the receiver you take majority. Whichever wins, you say that that is the one that is transmitted. The problem happens when, in this particular example, if the BSC ends up corrupting 2 out of 3 bits, which is happening in the 5th case, then the majority voting will give you the wrong answer. But hopefully that happens rarely. Most of the time, BSC will just mess up only 1 out of the 3 bits and then you're fine. If you think that BSC is really strong and it is likely to corrupt multiple bits, then what would be the recourse? What do you think should we do uh, if something like this, the 5th example, where 2 bits got corrupted out of 3, is likely to happen more frequently, then what can we do? So Kiran correctly said that, well, then instead of repeating it 3 times, maybe we'll repeat it 5 times, or 7 times, or 9 times. Why not 6 times or 8 times? We can actually do that. We can repeat 6 times or 8 times, but then because we are doing majority voting, we would like to kind of make an unambiguous decision. Just like in the tennis tournament or badminton tournament or any other even test series, it's always best of 5 or best of 3, right? It's typically not best of 4 or best of 6, because then what if both the sides win equal number of times? So here in majority voting, it's better to have an odd number value of n. So as you make n larger, then the chances become even smaller that many bits within the same block get flipped. And so then the chances that channel actually ends up corrupting the information bit, which is this bit, becomes even smaller. Right, so this we already talked about. The good decision strategy is the majority voting decoder in this particular case. Although the channel introduced so many errors, because we repeated it, we used this rate 1/3 repetition code. Most of those errors didn't matter, except the sequence of 2 errors here, because of which 1 bit got corrupted at the end. Okay. So what happens in this, we will see very shortly, is that when we repeat 1 bit n times, effectively we are doing something like this. For the case of n equal to 3, we have only 2 bits to transmit, 0 or 1 at a time. But we repeat the same bit 3 times, and so the receiver will get a block of 3 bits, which can have 8 different values as shown here. For small values of p, the most likely cases are 0, 0, 0 and 1, 1, 1, meaning that the BSC actually didn't introduce any error in any one of those 3 bits. And the next most likely possibility is that BSC messed up one of those 3 bits. So these are these 3 red colored arrows for x equal to 0 and 3 red colored arrows for x equal to 1 that I have shown here. But there is still some chance, not 0, but some chance that we transmit 0 as 0, 0, 0, and the BSC will corrupt it and make it 1, 0, 0 or 1, 0, 1, 1, 1, 0, meaning it will corrupt 2 out of those 3 bits. Or in the worst case, maybe all 3 bits. So you transmit 0, 0, 0, and the receiver gets 1, 1, 1. But that happens even with even smaller probability. The strongest is the green. Then the next strongest are the red colored arrows. And then all the gray colored arrows are pretty weak in terms of probabilities. If you assume that the gray colored arrows are so weak, then you will see that this case is sort of like this case, right? We still have some gray connection going from 0 to this 1, 0, 1, 1 and 1 to 0, 0 and 0, 1. But if we just assume that somehow those gray connections are not there, then we have achieved already what we want to do, which is turn a noisy channel into a noiseless channel. Okay. So now the question becomes, okay, so fine, this is all good, well and good, but what is the price that we pay? The price is that instead of sending 18 bits of actual information, that we actually are transmitting 18 bits, but the real information we are sending is only 6 bits. And so that is why this rate of the channel code is important. How many information bits you are transmitting, which is K, versus how many bits that you are actually encoding that data with, that is N. K can never be larger than N. At the most, K will be equal to N, in which case R will be equal to 1, which means you are not doing any channel coding at all. Otherwise, R will be smaller than 1. When R is smaller than 1, you are doing some channel coding, but at the price that you pay for that is that you are reducing the rate of information that you are transmitting. As we said, if we want to make repetition coding more and more reliable, we can keep on making n larger and larger, 5, 7, 9, etc. The price is that R becomes smaller and smaller. Okay, so let us do some basic math. I hope that this is all well appreciated by you. Not too much probability, but some little bit of binomial random variable that we have discussed in the earlier lecture. What is the probability of error in rate 1/3 repetition code? And that, as we have seen, will happen if either 2 out of 3 bits are in error or all 3 bits are in error. What is the probability of that happening? Well, 2 out of 3 bits can be in error with the probability given here. 3 choose 2, p squared times 1 minus p. And all 3 bits would be in error with the probability of Lakshman is asking, how is digital and analog communication different from fiber optics communication? So I don't know, Lakshman, again, this is similar to the difficulty I had yesterday. What in my presentation until now made you think of fiber optics communication? I mean, you can post some questions online, but should it not have some relevance to the talk that I'm giving? Otherwise, if you want to start a different topic on fiber optics communication, then I should stop talking about this. So I request you to please, I appreciate the feedback and the questions that you all post here. But if they are not relevant to the discussion that we are having, then I think it creates a very strange impression that it's like maybe you are doing it for the sake of distraction or what. Okay, so uh, if you take this expression and let's say you assume that the error probability of the binary symmetric channel was 10%, and then you evaluate this expression, it suddenly becomes 3%. Okay. There is nothing specific about this particular expression. You can easily generalize it to rate 1 over n repetition code, and that expression becomes the one given here at the very bottom of the slide. What does this equation say? That what is the probability of having n plus 1 divided by 2 errors, n plus 1 divided by 2 plus 1 number of bit errors, n plus 1 divided by 2 plus 2 number of bit errors, all the way up to all the n bits are in error. So you evaluate individually all of those probabilities, which are n choose k, p to the power k, 1 minus p to the power n minus k, simply the binomial probabilities. And then you add them up to determine your error probability for the failure of the repetition code. Now this is an expression that can be easily programmed into C++ or MATLAB or Python, and you can evaluate it. So I did that. As in this example, I assume P equal to 0.1, and I increased n from 1 to 3 to 5 to 7, so on and so forth. And what I'm showing on x-axis is the code rate, right? 1 over n. So when there is no coding, n is equal to 1, r is equal to 1, p is equal to 0.1. When we do repetition coding with rate 1/3, just a second. Sorry for the interrupt. So what this chart is showing is how the probability of detection error decreases as n increases, or the code rate r effectively decreases, right? So when there is no coding, you get 10% error. That is the error introduced by the row BSC channel. But if you put rate 1/3 coding, then that suddenly reduces to about 3%, which is the value that we have calculated here. If you do rate 1/5 coding, then that error rate goes down to less than 1%. If you do 1/7 coding, then it reduces to probably less than 0.03%, something like that. 1/9 coding, and then below 1/9, 1/11, and all that looks like as if it's pretty much zero. It's not zero, as we will see here on this chart. This is the same as this chart, but I made the y-axis logarithmic. So you can see that the error rate never becomes zero, but it steadily keeps on falling down and down. Okay, so at 10 to the power minus 5, what is happening is that although as many as 10% of your transmitted bits are in error, after encoding, only 1 in 1 lakh possibilities will be in error. So it's not completely noise-free, but you've made it pretty good in terms of being noise-free. What if you wanted to be even better than 1 in 1 lakh? Let's say you wanted to be 1 in a million, so you have to be somewhere over here. Or maybe 1 in a billion, so you have to be over here. Or 1 in 10 to the power 10. Right? So you transmit 10 to the power 10 bits, meaning 10 gigabits, and only 1 out of those 10 gigabits should be in error. If you want to do that, then your code rate should be around 0.025. 0.025 is how much? And will be about 41, let's say. So if you take each bit and repeat it 41 times, here I've taken n to be all odd values, so it's not 40, it is 41. If you, or 39, whichever. So if you take one bit and repeat it 41 times, then even though the binary symmetric channel is corrupting the bits at the rate of about 1 out of 10, you will be able to transmit as many as 10 gigabits before one bit gets corrupted. And so that is the power of the simple repetition coding. It makes sense. If you are repeating one bit 41 times, what are the chances that all 41, or sorry, half of those 41, right? Because we are doing majority voting. What are the chances that, let's say about 20 or 21 or 22 or more than 20 bits out of this 41 get flipped by BSC? Pretty low chance. Exactly this much chance, 10 to the power minus 10. If you want to get an error rate of 10 to the power minus 15, then according to this, we need about 0.016 rate, which corresponds to n equal to 63, meaning that repeat each bit 63 times. That is correct. So we are assuming that the errors are independent of each other, which is more or less a realistic assumption. Most of the time, the channel does not remember that, okay, it did not corrupt the previous bit, so now it shouldn't corrupt the current bit as well. Or it corrupted the current bit, so it should corrupt the next bit. That is typically the case for many of the real world channels. They are memoryless. Hello? No, not now. Okay, so what was I saying? Yeah. Many of the real world channels are memoryless. There are some channels which are not memoryless. They are called fading channels. So there, sometimes the receiver enters some shadow or some blockage or some fade scenario, where suddenly a block of bits gets corrupted before the receiver comes out of the shadow and so on and so forth. Right? If you're talking on your phone and traveling in the train and the train goes through a tunnel, and then if the tunnel is not too long, then during the time that you're talking where the train is in the tunnel, you will have this type of shadowing or blockage induced loss, where suddenly a big chunk of bits that are transmitted got maybe erased or flipped or something like that. But there are methods to turn this type of correlated noise channels into uncorrelated channels, and those require use of some random interleaver techniques that we won't get into right now. But for the time being, we can assume that all of these errors are independent. Okay. Now, I think I have maybe 15 minutes, so I'll take maybe one or two topics uh, before we conclude this lecture. So the question that I will now ask you regarding this is, so fine, repetition coding can do something like what we want to do, but just like the question that we asked, what is the best achievable data compression in the context of noiseless channel coding? There the answer that we got was that the entropy is the final and the ultimate answer as to how much you can compress any source. If you want to recover the compressed, from the compressed data, if you want to recover the original data faithfully, if you don't want to lose any data, then you cannot go below the entropy in terms of the average number of bits per signal. For the noisy channel coding, let's see what could be a similar answer. And so toward that, let me ask you this. So we are going to consider for this question the same binary symmetric channel that we've been modeling all along. For the sake of simplicity, let us assume that this crossover probability P is known at the receiver. Okay? We'll just assume that receiver somehow knows the value of P. It makes things simpler. So this is actually a good thing that we are doing. In reality, it may not be, this knowledge may not be available. But even when it is available, let us say what is the best we can do. Let us say that a transmitter is transmitting 1000 bits per second and all these bits are random. So they become 0 and 1 with equal probability. Q is equal to 0.5. So my question is that suppose when an ideal channel where this crossover probability P is 0, what is the rate at which the information will be received? Transmitter is sending 1000 bits per second. P is 0. So what will the receiver be able to receive in terms of the bit information? Did you get the question? Yeah. So Venkat gives right answer that P is 0, meaning no bits are getting flipped. If the transmitter is sending 1000 bits, the receiver will also get 1000 bits every second. Fine. So now my next question is, suppose P is equal to 0.1. So now in this example, I increase the value of P and made it 0.1. In that case, what will be the data rate that the receiver will be able to get accurately? So Matthew said 900, 900, 900. Okay. Pooja said 900. Okay. Now let me ask you the one more question that suppose, so for P equal to 0, it is 1000. For P equal to 0.1, you say 900 bits per second. Let's say P is equal to 1. Okay. Then what do you think? And suddenly I got a lot of answers, 0, 0. But now Matthew said 1000. Now, remember, we said that the value of P is known at the receiver. So if the receiver knows that P is equal to 1, it knows that all the bits that it is getting are flipped. So all that it will do is just unflip those bits. And then it will get those 1000 bits accurately. Right. So then the strategy that you had where you said that when P is equal to 0.1, I should just take 10% of the bits that are being transmitted. I have to throw them out. The remaining is the reliably received bits. That couldn't be true, right? Because then, according to that answer, when P is equal to 1, you should get 0 bits of information. So that is not happening. So there is something wrong with this approach, which says that the value of P at which the rate of information transfer becomes 0 is equal to 1. That answer is not right, because when P is equal to 1, actually BSC becomes deterministic. And therefore, the receiver will actually get full 1000 bits per second. the other answer that when there is p equal to 0.1, you get 900 bits per second, that actually is also not correct, because this formula doesn't work, 1000 times 1 minus p, right? The problem is that the receiver knows that the channel is flipping 10% of the bits, but it doesn't know which 10% were flipped, right? So it got 1000 bits, but how does it know which 100 to throw away and which 900 to pick? If it knew that the channel flipped exactly some specific 100 bits, then it will just unflip them and then you get full 1000 again. The problem is that the receiver does not know the location at which the bits got flipped, right? So that's why this answer of 1000 times 1 minus p does not work. So what actually works is the notion of information transfer. Okay, so what is information transfer? And so for that, let me see how much time you have. Maybe 5 more minutes. So let me just quickly say that there is a notion of mutual information or information transfer that we were supposed to study. Actually, I have it in the topic 2, information and entropy slides, where we define the entropy over here. There's this formula. And then there is the notion of conditional entropy that we should consider, which says that the entropy x, entropy h of x of a source, if it kind of is analogous to the temperature of the source, then the question is, what is the entropy of the source after we obtain the output of the channel Y? And that is called the conditional entropy, entropy of x given Y. Okay? And then the notion of information transfer says that the entropy x given Y should hopefully have reduced compared to entropy of x. Because if it did not reduce, then somehow the information did not actually even get transmitted in some sense. See, if you are at the receiver, if you don't know what the transmitter state is, that uncertainty that you have at the receiver relates to entropy of x. I don't know, you might have many times faced the situation that you took some very important exam and your result was going to be announced. The day before the result was announced, you had uncertainty about what your result is going to turn out to be. Right? So that is entropy h of x. When the result got announced, you heard or you saw or you got some email or WhatsApp message or something that became Y. Through that, your conditional entropy of x given Y hopefully reduced. Maybe it effectively became 0. That message was very reliable. Then as soon as you received Y, you exactly knew how you scored in that exam. Once the uncertainty vanishes, entropy becomes 0, as we have seen. And so whenever information transfer is successful, Hx of y, Hx given y, entropy of x given y, becomes smaller compared to entropy of x. And in the information theory, the way information transfer rate is defined is the difference between the unconditional entropy, the entropy before you knew the result, minus the conditional entropy, entropy of x given y. Entropy of x after the result was conveyed to you. In most of the cases like this that I'm describing, entropy of x given y becomes 0. And then the full amount of information equal to entropy of x gets transferred to the receiver. But it could also be that maybe the friend who is sending you your result is a little bit naughty. And so most of the time he's good, but sometimes he plays mischief with you. And so you ask your friend to collect your result, and so he calls you and says, oh, you failed. And so you are really depressed, but you have faint hope of hope that maybe he's pulling your leg. And maybe you pass, but he's just playing tricks with you by telling you on the phone that you failed. So even when he says you failed, you have some uncertainty about your actual exam performance. Entropy of x given y has not become completely zero. That's why you have that faint ray of hope. So in that case, this difference will not be exactly equal to h of x. It will be some difference, h of x minus h of x given y. So coming back to this example, what we will see is that the answer about when the information transfer rate becomes 0, what are the information transfer rates when the values of P are different, all of that are nicely answered by using this formula, not 1000 times 1 minus P, but the information transfer formula, which is entropy of x minus entropy of x given by the difference. And you can do the math very in a straightforward manner. I have done the derivation in the slides, which you have access to, so you can take a look at them. But what turns out is that the amount of information that gets transferred over a binary symmetric channel as for different values of P behaves in this manner. This is exactly the inverse of the entropy curve that we had drawn. What does this say? If the binary symmetric channel has a P value which is either 0 or 1, full amount of information gets through. If it sends 1000 bits, all 1000 bits get through. Over here or over here. When P is equal to 0.5, meaning this BSC messes up half of the bits on random, that is when it is the most corrupting channel and your information transfer becomes 0 at that point. Otherwise, we consider p-value of 0.1. For 0.1, the answer is that about half of the bits that you are transmitting will get through. What this says specifically is that in this repetition code example that we had, in order to make the error rate become 0, we had to reduce the rate to very small numbers like 10 to the power minus 15 or so. What this analysis says is that if P is equal to 0.1, then your rate, which is this information transfer rate, doesn't need to be any less than 0.5 for you to get error-free message delivery. The achievable rate becomes this red colored line instead of the blue colored line. The repetition code is highly inefficient versus the actual achievable result. Okay, so with that, I will stop here, and sorry, I've taken a few more minutes. Professor Rajendra will take some 5 minutes of break before I start the next topic.
Yes, sir. We can take the 5 minutes break. So Rajendra sir, yes. Can you hear me?
Yes, yes, I can hear you.
So we can take 5 minutes break.
Okay, so
Thank you.
I'll see you all after some few minutes. Okay.
Sure.
Thank you.